So plenty of time for our education session here. So we have Brendan Duncan from Unity, has done some really great work on bringing Unity to the web. I was going to talk a bit today about WebAssembly, WebGL, and WebGPU. I think Brendan and I, we met recently at the WebGPU and WebGL meetup in San Francisco, I think co-located with GDC. And he just had a ton of really good insights on bringing a native code base that's graphics, to the web, and especially things around the shaders and debugging. So I just thought it was super insightful and wanted to hear more. And Brendan was kind enough to come back and beyond working at Unity, he formerly worked at Disney Animation, PDI DreamWorks, Google, and Apple. So Brendan, we're super lucky to have you. Can't wait to hear your talk today. So I'll stop sharing and over to you.
All right. So like Patrick mentioned, my name is Brendan. I have been at Unity I just had my 5th anniversary, so 5 years. So I'm still in my toddler tantrum phase, but I can dress myself. So I'm getting older and wiser, I hope. And the whole time I've been at Unity, I've been focused on the web as a platform. I joined the web platform team, and a couple of years ago, switched over to platform graphics, where I focus on the website of graphics. So making sure all the graphics work on the web using WebGL and now WebGPU. And so I was going to do this little talk about, how we get Unity onto the web. Unity is a very large game engine. It's I don't even know how many lines of code. It doesn't even matter at this point, but it's a lot. And how do you get something that large onto the web in an environment where a person can create their game and play it on the web and have that to be a good experience? So the web is, for me, it's a love-hate relationship. I love the web. It's an awesome, amazing platform. It's this, ideal, share it with the world, not having to deal with app stores, all these type of things that, you can make a game, you can make an app, put it up, it's accessible to everybody. At the same time, it comes with a ton of challenges, and it's a little bit like dialing the technology clock back 20 years as far as performance and memory, and you miss the days of having a desktop app where you can just do an app open and open a file. You have to invent new solutions to things that you normally take granted for. And I enjoy that aspect of it. So just a quick overview of Unity. It's a real-time engine. It's typically a game engine, but it's used for a lot of other verticals like architecture and automotive and all that kind of stuff. But its target audience has always been as a game engine. And one of the things about Unity as an engine is that it has I have to keep myself from swearing here. It has a lot of backends that it supports, different platforms and technologies that it supports. It's probably over, this slide is a number of years old now, but it supports, mobile and desktop and consoles, Xbox, PlayStations, VR, all these different technologies. And one of the technologies is web. So you can build your game. It's kind of like the Java of game engines, write once, run everywhere. So the idea is you take everything that you make in your game, including the engine to play the game, and you get that onto the web. And that's the challenge. So how do we do that? So the main compilation system that we use is Emscripten, which takes C and C++ code and it compiles that into WebAssembly. And it does that through LLVM compiler toolchain. It's got a lot of frameworks involved with it, so it's a typical toolchain for generating WebAssembly. So we have all our Unity engine code, which is quite large, and that gets compiled into static libraries, essentially. All the user code and kind of outside of the core engine is actually written in C#. Emscripten normally does not compile C# into WebAssembly. There's some advances now, but how do we get all the user space code from C# into WebAssembly? So we have a in-house toolchain called IL2CPP, and it's a ahead of time compilation process that takes .NET bytecode. It does a bunch of stripping for that to get rid of the stuff that's not actually used. And then it translates the .NET bytecode into C++. And once it's in the C++, then we can pipe that into Emscripten, include the engine core libraries and all the, if the user has any plugins, C++ plugins or JavaScript plugins, to feed that in, and it all gets put into this black box compilation process, and it spits out WebAssembly. And the other aspect of it is all the content of the Unity project, which is all your meshes and textures and shaders and all those type of things. We have to translate that into the target platform. So there's big compilation tool chains to do that. And what you end up with in your build is a big WebAssembly file and a big data package file, which is the data necessary to start the game or app, and some bunch of JavaScript framework stuff, which is all the calls from WebAssembly into JavaScript, which is what communicates with the browser. So that's kind of this magic process that you can open the HTML that comes out of this process, and the game that you had in your editor is now running in the browser. It's a little bit magic. It's a little bit miracle that it works, but it does, and quite happy that it does, because otherwise my job would be a lot harder. And not to say that there isn't issues. People invariably try to do things that are not compatible with the web. We'll try and open a file or do something that there's no equivalent API for on the web, and get yelled at about that, but we just tell them not to do that and move on. And we try and find solutions when we can, obviously. Anyway, so some of the new technologies coming out of WebAssembly that are quite useful for us is, and just these are just a couple examples, is we now have increased 4 GB memory address space in WebAssembly. It's traditionally capped at 2 GB because a lot of the pointer indexing was signed integers, 32-bit integers, and you capped at 2 GB, and some other things with WebAssembly. So recent advancements in WebAssembly let us now access 4 GB. It's a little bit ridiculous, in my opinion, to use 4 GB of memory for a web page, but sometimes you gotta do what you gotta do, and you can make some cool stuff with that. The browser is obviously in charge of making sure you don't overwhelm the system. Some of the other things is there's been a lot of advancements in using SIMD intrinsic operators to do faster math operations and things like that. So we can automatically take advantage of those new WebAssembly operators. All the code that was written in SSE or Neon in handwritten SIMD code in the Unity engine automatically gets translated to WebAssembly SIMD operations, and you get the performance benefits from that. And they can be quite significant performance benefits from that. And the third thing is multi-threading. WebAssembly is typically a single threaded execution. It was multi-threaded for a long time, but then we got hit by Spectre and other type of issues, which the bad actors out there ruined all the fun for all the people that just want to make cool games. So we lost multi-threading for a number of years. It's coming back, or it has come back. And so we can enable multi-threading for the C++ or the C side of the engine and user code. The problem that we still have is a lot of the user code is written in C#. C# does garbage collecting, and because of security issues with WebAssembly, it doesn't allow you to access stack traces and other things necessary to do mutable threads, garbage collecting within them. So it's just an unfortunate limitation until we can figure out a better garbage collecting situation. But you do get at least C++ multi-threading, which helps out all the engine code and does make a difference. So the graphic side, which is the part I like, is we have two graphics APIs that you can use for targeting the web. The normal one is WebGL, which is essentially OpenGL ES for the web. And Unity was originally written on top of OpenGL back in its original form. It since has a lot of different graphics APIs that it supports: DirectX, Vulkan, Metal, all the platform-specific ones, PlayStation, Nintendo, all those. So it's always had an OpenGL driver for it and OpenGL ES specific driver. So we can, because WebGL is just written on top of, is compatible with Glaz, more or less. We can use the Glaz driver in Unity. We do some checks for am I WebGL? If so, don't do the stuff that's not supported by WebGL. And mscripting takes care of calling the GL functions, passing that into WebGL, and it just automatically works. Shaders in let's see, the shaders in Unity are typically written in HLSL, DirectX shading language. So we have to have a shader compilation process to translate to the target platform, whatever it is, whether it's Vulkan, in this case, GLSL for Glaz. So we have a shader compiler that does that. For GLSL, we use FXE HLSL CC, which takes the DirectX bytecode out of FXE and translates that into GLSL. And then we do some massaging of the GLSL after the fact and make it all work. And so we use, platform defines a lot of different places to make sure that for any given platform that we're not doing something that it shouldn't be doing. And the end result of all of this is that you just get to play your game on the web, and I'm stoked to that it does. So some of the things that we can do is one of the things that Unity has is something called SRP Batcher, which is part of our scriptable rendering pipeline, URP. What it does is it can batch drawing calls, but not only for the cases where you have you're rendering like the same shader with multiple geometries, or the same materials with multiple geometries, but it can actually batch together draw calls for where you have two different geometries with the same shader that have different materials assigned. So like a red sphere and a green sphere, for example. But to use that, it requires some features that are in GLES 3.1. WebGL 2 is GLES 3.0. It doesn't have some of the features of GLES 3.1. It doesn't. In this case, the feature that SRP Badger needs is binding locations and uniform layout locations, because when you have different objects with different materials, we have to make sure that there's a consistent layout for where the buffers are located and the textures samplers are located, so that we can write to it once and then blast through all the draw calls. Unfortunately, WebGL doesn't have that feature. It's one version shy of having that feature. So what we did, my co-workers, Yuka and I did, is we wrote a way to work around that. So we did this as an Emscripten extension. So we put it in, Yuka is one of the developers for Emscripten, so he put it in there and he wrote an extension for it. And so what it does is we pre-process the shader as it's coming in, and we extract that information. We change the shader so it removes that information. So now the shader becomes compatible with WebGL. But now we have the binding locations and layout locations stored in Emscripten's WebGL layer. And so when you do things like binding a uniform buffer or binding a sampler, it will translate the locations for where WebGL has dynamically created those locations into what the explicit locations are. And that automatically works. And in the case where you're trying to, we get significant performance benefits out of being able to batch things this way. In a worst case scenario, frame rate was going from about 5 frames a second to 60 frames a second. Significant benefit from being able to do that. And so this is all part of Emscripten now, and I put a link here for the extension that you can put into Emscripten, and anybody can take advantage of using it. Requires command line argument when calling Emscripten to enable that feature, because don't want to do things unnecessarily for people that don't need it. So WebGPU is kind of my passion project for the last few years. WebGPU is a new API for the web, graphics API that is modeled after modern graphics API. So you DirectX 12, Metal, Vulkan, that generation of graphics API. So WebGL is modeled after the classic OpenGL, which I still love, but the new APIs do things more object-based instead of stack-based and state-based. And there's a lot of advantages to that. They also added things that they decided never to add to WebGL, which is compute shaders and direct drawing and all these more advanced features. And so we can utilize that quite extensively inside of Unity. And so I took it, I started the WebGPU as a Hack Week project a number of years ago, and it's turned into a real thing. I'm super excited about it. And so we have the WebGPU driver in Unity 6 in an experimental form, and we're just continuing to invest in it. I'm super excited about that. So we couldn't use, with WebGL, we could use the GLES driver, and with WebGPU, couldn't. There's no equivalent existing API. You can't leverage Vulkan or Metal or any of these. It's its own unique thing. So I had to create a new graphics driver for that. Had to create a way to call into the JavaScript side, so a custom Emscripten layer. The WebGPU group has written their own Emscripten API for WebGPU, but we use our own, which is also open source. We did that because we wanted to make sure that we could get maximum performance out of that, reducing garbage collecting, and a couple other nice little features. We have to have a custom shader compilation process, which is just bonkers right now. We go through from HLSL, go through FXC and HLSSC to GLSL. That goes through GLSlang to create SpearV, and then we can pipe SpearV through Google's shader compiler Tint, which will generate WebGPU shaders. It's a crazy complex shading compilation process, but it works. In the future, we're going to use DXC and reduce the compilation process, but that's another can of worms. But it's in the works. And so we've been working closely with the WebGPU Spec Committee and Google and Apple to make sure that WebGPU can handle an engine the size and complexity of Unity. And there's been a number of challenges in that and things that we've had to ask the spec to change or improve on. And they've been very receptive, and it all just magically works. And now we can take advantage of all these new features of Unity, like VFX graph or GPU-driven particles and GPU-driven skinning, and we can get some really cool stuff out of that. Debugging graphics on the web is difficult, to say the least. So on desktop, you get spoiled by tools like RenderDoc or all these other Insight, all these other great tools for being able to debug what's going on the GPU, but you can't. There are ways to do that with a browser, what it's doing, but it's not super easy, and it doesn't always tell you what you want to know, because there's translation happening between going from like WebGPU to its backend. It'll have a backend of Metal or Vulkan or DirectX. There's indirection there, which isn't exactly what you always want to know. So I just took it on myself to write a new debugger. WebGL has some great tools like Spectre.js that doesn't exist for WebGPU, so I had to create a new one. And so this is open source on my GitHub here. And some of the things you can do is frame captures. You can dig into what the content of buffers are. You can inspect textures and all these other shaders and all these other fun type of things. I basically went through RenderDoc and tried to mimic as much as I could. And so I use this for debugging in Unity all the time. I'll do a desktop Vulkan build, and I'll do a WebGPU build, and I can step through the frame capture and look almost command to command, buffer content to buffer content, see, oh, I made a bug here. I missed the offset to a buffer is wrong or whatever. And it's been super helpful for debugging graphics and figuring out why a black screen is black when it should not be black, which is, I typically spend a lot of graphics programming. And so that was my whirlwind talk about getting Unity onto the web. Just to call out to the Unity webpage for our web solution, because I'm a true believer in web as a platform, and I think it truly is a first-class platform for writing games and apps. And I'm excited about all the evolution of the web and all the cool, awesome things coming out, WebGPU and WebAssembly and all these type of things, which let us do things that were just unimaginable before on the web, and turn that into what it should be, the next great platform. And that's been the promise of the web for a number of years now. So thanks, and I'm happy to take questions.
Brendan, that was awesome. I wrote down about 8 questions. But who has the first question?
Yeah, hey, thanks for the presentation. I've been looking forward to this. I'm just curious, it looks like all of this is ready to go. I could use it today. Is that the case?
Yes, that is the case, yes.
Okay, great. Thank you.
So if you download Unity and you set your project to use the web as your build target and build run, it all works, and it's used quite extensively by a lot of different types of projects, not just games, but all sorts of things. And it's always as a developer inside of Unity, we don't like track what people are doing with Unity. So when people show, the things that they're working on, that's the biggest thrill I get, is just seeing all the cool stuff coming out of it. Sometimes they'll do that as a bug report and I'll have work to do, but it's still exciting to see.
Other questions for Brendan?
Hey, Brandon, this is Jordan. If the Unity C# code is making calls into DLLs that are written in C++ and export C functions, are there any issues with that working with your pipeline?
The DLLs are a little tricky. This is all just due to what mscripting can do. So you can link in static libraries for sure. When it calls out into a DLL, obviously that has to get translated into WebAssembly, and if it can't, then there's no DLL that exists that you can load on the web. So then that would be something you cannot do. So static libraries for sure, because the compilation toolchain sucks that in. Part of the linking process, and the output of the linking process is WebAssembly. DLLs are a little trickier.
See, Neil has a question.
Yeah, thanks, Patrick. Hey, thanks, Brendan. Thanks for the awesome presentation. Question on the formats, because with the GLTF USD interoperability, I know you're mainly focused on the runtime, perhaps. So do you interact at all with USD or GLTF, or trying to get them to work together? And anything we can do to help there?
So yes, those formats are obviously super important, and at the point of the engine running on the web, there is no more GLTF or USD. What happens as you bring in GLTF and USD assets into your project, there's a whole asset compilation process that sucks those ins and generates the runtime asset data bundles from that. So there we have a whole asset import process that comes along with that. There's not a lot of with that happens at runtime, because you don't want to decode GLTF at runtime. You take the hit of decoding it. If the assets are in a state where you can just load it into a buffer and draw it, which is essentially what GLTF is designed to do, but do that specific to Unity, then you don't take any of that loading hit and you just draw. So in the data bundles at runtime, it's already been processed. USD is obviously more complicated. You have to do all the things with resolving the scene graph and all properties and all these type of things. So it's best to do that at load time. But as an asset interchange format, obviously it's super important to Unity, and there's been a big push to improve the ingestion of GLTF and USD inside of Unity because, I mean, sure beats OBJs.
Okay. Yep. Cool. Yep. Thank you.
Henrik has his hand up.
All right, yeah, thanks. A great presentation. This is super exciting. So, can you say something about what is the size of the WASM binary, and are you doing any particular optimization to kind of improve the startup time on the first like download of the actual engine, ignoring all the content for a game?
Yeah, so startup time is, I think, one of the most important parts of having something on the web. People that browse the web are not very particularly patient. You load a game on, your Xbox, and you'll sit there for 10 minutes and you're happy to do so because there's an expectation with that. But you go to a web page, and if it hasn't loaded within a certain amount of time, you just move on. Especially for things, if you're doing like banners or anything like that, you don't want to do that. So load times is super important. The WebAssembly side of things, we have a lot of stripping that goes into it. We're stripping unused code, and to try and get the WebAssembly to just what you're actually doing, that's easier said than done. There's a lot of challenges to that. A lot of times you'll strip too much, or the tools to do that aren't super great. And there's other things that go into that, like things that you can do at runtime, so you don't know if you're going to need something or not. It's challenging, but there's a huge amount of work that's happening now into that stripping process to reduce that code size. There's already some that exist now, but there's a lot more work that's being done on that. If you just take like Unity 6 now and you build an empty project, the WebAssembly side is probably, I don't know, might be like 5 megs or something, which is in my mind still too big. But that's where that work is going into, is to reduce that. The other aspect of it, besides the WebAssembly, is the data. So the assets in your game, the geometry and shaders and textures. So if you just take a project and you throw it all into your Unity project and you build and run, all those assets are going to be put into your data file, and you can potentially have a very large data file. The WebAssembly and the data file and the JavaScript all have to be downloaded before the game can start. So those are all the things that contribute to startup time. The thing is that we're basically giving the user a hammer and a nail and they can design the project how they want. So we have a lot of tools to help address that. So we have streamable assets, things like we call addressables, asset bundles, that can be downloaded after the fact at runtime. So the ideal goal, and what we try to help people do, is to get your initial content of your game and the data that goes into it as small as possible, to as much stripping of the WASM as possible, and as much as minimal assets as possible into what you're going to be loading initially, so we can get something on the screen as fast as possible. And it might just be like a loading menu or something like that. And then as the initial screen is on, we can, the project can download and stream in assets through these asset bundles. And then, so you can load the first game's assets or whatever, enough to get going. And so we can do that after that initial screen is loaded. We have, some best practices and things like that, and we try to help people to do that, but it's ultimately on the user, and they can choose to make a game that's a gigabyte download, or they can choose to spend the extra time to optimize it for the web. And so those are making that process of let's optimize it for the web is the tools that we're actively working on improving and helping people with to make better choices for that. A lot of people will take a game like, well, it runs on my desktop, switch the platform to web, build and run, and they get a 2 GB game. It takes, 15 minutes to load, and they're like, what's wrong with the web? This sucks. Well, we have to think about the web as a platform and not an afterthought. And so those are the things that we're helping and improving on. And it's a constant battle, but it's an important one.
So any particular tools that you found useful there in stripping down the code, like to getting that down to like 5 megabytes now?
Yeah, so some of the things is like the user will have packages, third-party code, libraries and stuff in their project, or they'll do something that they don't know that they're doing. So for example, if you just create an empty project and you put a sphere in the project, a sphere object by default will include a physics collider volume around it. It's just drawing a sphere, but because there's a physics collider object on it, it has to pull in now the whole physics module. So like, why is my project that's just drawing a sphere, well, big? So we can provide tools, and we have some that exist that says, what are all the things, all the Unity modules and things like that that are going into this build? And you're like, well, why is the physics module being pulled in? I'm not doing any. And then we can say, oh, your sphere has a physics collider on it, and that physics collider exists as part of the physics module. So that code is coming in. So we're working on a lot of tools for this module stripping and all these things that contribute into that not just try to automagically do the stripping and reducing, but also provide tools to let the user know what's actually happening and where that data is coming from.
So that's mostly in-house tools then to kind of figure out those dependencies. There's no like, part of the Mscript tool chain or other, tools out there that could help with code analysis and stripping out that code.
Certainly, Mscript linking stage is an important part of that. Part of the problem is also when you start getting into that level of, stripping and analysis at the compilation process and linking stage can actually take a significant amount of time. And so we have, a developer mode where it minimizes what the compilation tool chain is doing. It doesn't do any symbol stripping or anything like that. And so for working and iterating, you can do that. And then you can turn on like optimize for size, maximize linking, and it can take a good 15, 20 plus minutes to build your project. But then that's what you want to do for a release build, because then you're maximizing you're maximizing the stripping, minimizing the data sizes. And so we have some best practices guidelines for, what settings should you use when you're developing, and what settings should you use for your release build. And then that also includes things like, texture data, where you can and when you can use texture compression. Texture compression on the web is still a bit of a mess because it still uses underlying, platform texture compression. So you have your ASTCs and ETCs and all these other types of formats. And so then you have to worry about what platform is your web page running on, and download the assets for that particular, so you can maximize or utilize platform-specific texture compressions and things like that. So it's all a big challenge, but it's, providing tools to simplify this very complicated process is the goal. And
Yeah, thanks a lot. Yeah, I'll let Phil go next.
Phil?
Yeah, thanks for the question. Maybe something a bit in line with what Henrik just asked. I was wondering if you had any options for, either bundling engine specific data into something that could be hosted on on the CDN or cached locally, or how tightly was the actual game data and game logic and engine logic coupled as part of the final bundle that you produce?
Yeah, so that's a great question. A lot of research has gone into that. There is some work being done to investigate how to do that in a great way, in a universal way. One of the problems is, it would be ideal if you could host just the engine part of the code, and it'd be version. So when you have your game, it says I use version, some hash, and you have a hosted CDN that then says, oh, here it is, or you already have it cached, I don't need to do it. The part of the problem is that web bad actors have ruined web for all of us, which means that caching and CDNs and all that stuff only work on per site basis. They don't work cross-site. And so you have all these cross-site origin attacks and all these type of things that the browsers have to constantly protect you against, which means that you could do that. You can host the engine on a CDN, but it would only help for wreloads of that game. Your browser is already caching reloads of the game. It has a local cache. And when you go to that site again, it's in your browser cache. And if you haven't cleaned your cache and things like that, then it'll reload from cache. And second runs will be significantly faster. First runs are always the most important run. That's where you get your first impressions. So you don't get the benefit when you go to a site, even though, you could have a CDN with the engine, it would still have to download it again because it wouldn't respect to that cache. So a lot of research going into that, but it's no easy solution to it.
Yeah, makes sense. Oh, thank you.
Yeah, I'll go again. So this is a question from one of my colleagues that couldn't join the call. So where is the rendering happening? Is that in the main thread or is that in worker threads?
Yeah, it's a good question. Right now, it's in the main thread. There's work being done to pull that out into a worker thread. There's complications with that, but it's an important thing to do, and it'll happen in the future. Right now, it's in the main thread.
Okay, thanks.
And Brendan, in the future, are you talking about building up and dispatching commands or just building up of buffers?
So there's a couple of different ways to do it. One, you could well, one of the promises of WebGPU going into the future is threaded rendering, which means that you could do command buffers per thread, and you can multi-thread rendering in that way. You can do off-screen rendering where you have an off-screen canvas and you have a worker thread, and you do all your rendering in that worker thread. You render into the off-screen canvas, and the main thread presents the off-screen canvas onto your on-screen canvas, and you can pull off all your rendering that way. So that's the way that you typically do off-screen and off-main thread rendering. Right now, it's a complicated to do that. It's not trivial. One, you don't have access to all the DOM elements. So we do a lot of stuff with audio, and we do a lot of stuff with other types of things that are run by elements on the DOM. You don't have that in your worker thread, which means that we really would need to have the entire engine on the worker thread and communicating through messaging to do anything that interacts with the DOM. These are all things that are being worked on to find a best way to do that. There's complications with that. Off-screen canvases have only recently reemerged into the browser ecosystem. Safari WebKit, took a little while to get support for them and other types of things. So it'll get there. You kind of needed to wait for the browser ecosystem to be there, and then all the work to take a giant engine and move it off thread, do all the message passaging, which comes with overhead and downsides as well. But it'll be an important thing to do.
So if one were building a high performance real-time engine today, and a primary target, or maybe the main target, was the web, do you think that scripting, WebAssembly, and WebGPU is the way to do it, or is it TypeScript, or is it something else?
I think there's pros and cons to both of them now, so that's not a simple question. Obviously, if you take an existing engine like Unity, which is a C++ engine, there's no alternative solution to it except for maybe translating everything that you're doing into the engine into some sort of equivalent JavaScript code, which there are projects that do. If you were making a high performant engine, TypeScript, which is just JavaScript. JavaScript is, I love JavaScript, and it's a very performant language and runtime, and increasingly so. There's advantages to that, tool chains and all those type of things, iteration times, lightweightness of it, because you're writing a custom engine. So you have all these amazing existing engines out there like PlayCanvas and Babylon.js and 3JS. I'm huge fans of all of those. And there's no right way to do it. If you're doing something that scales and can scale to the complexity of Unity there are significant advantages to WebAssembly and doing things that way that I don't think we could write everything that we're doing in Unity through the WebAssembly player. I don't think we could do with a JavaScript equivalent, but not to say that you can't create an awesome engine with JavaScript. That was my very diplomatic answer, but I believe it.
Yeah, totally. I get it. What other questions that folks have?
Downside to unscripting. I get to rambling, so sorry, cut me off. Downsides to unscripting is obviously the compilation process and complexity of managing that. You have a little bit less control over the output of it because you're relying through, tools that generate the WebAssembly. So how big that WebAssembly is, and it takes a lot more care to generate something that'll load fast as well as execute fast.
Yeah, if no one else has any question, I can go one more. So you support both WebGL and WebGPU. Do you see like a need to maintain WebGPU for a certain period of time, especially with the compatibility mode in WebGPU? Like what's your kind of reasoning there? Or like, do you need both, or would it be good to bet on WebGPU only at some point?
Yeah, to clarify, you said maintain WebGPU, but maintain WebGL.
Oh, yeah.
Compatibility mode will help address a lot of the issues with WebGPU as far as reach goes. So compatibility mode for WebGPU is that they are writing a GLES backend for WebGPU, and it can reach the platforms that Vulkan doesn't reach. So Android phones that are not Vulkan compatible. It'll help address that. So there's two parts to that question. Yes, I see the need to maintain and care for and love WebGL for the foreseeable future, because WebGPU is still new. It's a couple of years old now, but browsers take a long time to come up to speed, to get all, the spec solidified, all the conformance tests running, passing on all the different browsers. And so there's that aspect for it, and that it's not ubiquitous across the web. And if you want your game to have the maximum reach, WebGL is currently the only solution. That's quickly becoming less of an issue because everybody involved with it, with WebGPU, deeply cares about WebGPU, and that includes Google and Apple and Mozilla are the three main browser companies right now. And Google has been ahead of the game for quite a long time because they have a lot of resources to put into investing into WebGPU, and Apple has been kicking butt recently with their development of WebGPU, in that I submitted an issue to them and they're coming back within sometimes literally minutes. Oh, got that fixed. And it's rolling out into Safari Tech Preview, and it's rolling out into iOS 18 betas. And we had all these issues running Unity content. It's running great now. So they've been really pushing ahead. We're having a little bit of troubles with Firefox and Mozilla, but they'll get there. And I'm not worried about that. So getting the ecosystem down, we're maximizing the people being able to use it. WebGL is still super important for that, for some distance into the future. The other aspect to that is that even with compatibility mode, WebGPU still has some limitations, even compared to WebGL. And things like WebGPU does not have synchronous readback. If you just say, in an OpenGL or WebGL, GL read buffers or read texture, get pixels, whatever, you get the data immediately back. The browsers hate that because they are implementing on some backend, whether it's Glaz or some other backend, and you're stalling the GPU, but you're also stalling the CPU. And there's some cases where it can be a very significant stall. So when they designed WebGPU, they're like, let's not repeat mistakes of the past. They got rid of synchronous readback. So you can only say, get me this data, call me when you got it. And you get an asynchronous readback, and they're able to manage that much better. You don't stall the GPU, you don't stall the CPU, all these good things, except for there's a huge amount of code out there with people doing things the old way because that was the way to do it for a long, long time. We have a lot of code in Unity written over the last 15 years that people doing things the easy way and not the good way. And there's other limitations like texture formats and things like that. WebGPU is this lowest common denominator between Metal and Vulkan and DirectX, and the things that aren't, don't cross that Venn diagram of the middle get excluded and then can come in as extensions later. Well, they don't have extensions for all the things that WebGL can do because they were either just supporting it or emulating it. And sometimes they emulated it very poorly and slowly, but it was there, you could still do it. And they don't have all of that stuff on WebGPU yet. It'll get there, but I don't see a timeline for all those things coming together yet. So I still love WebGL. I'll maintain it, and I'll fight off all the people that say that we should dump Glaz because it's too much of a maintenance cost. We have to do it.
Nice.
Great. Look, I love all the discussion. I see a question here. Before we go to the question, though, so we're just a few minutes over on time. So, Brendan, if you have time, what we usually do is we end the meeting, but then we end the recording. What we do, a water cooler, and people still hang out. I have like 10 more minutes, maybe to help host that. Brendan, would you be able to stick around a little bit if we wrap up the official meeting and still chat?
Happy to do so.
Cool. Well, then first, before we end the meeting, let's do an applause. Thank you so much for sharing everything.